Thank you very much, Andrew, and good night, good evening for everyone. So my name is Franciele, and yeah, so I'm actually gonna change a little bit of the dynamics of the astronomy on tap, but I think that fits for the occasion. So this talk actually that I'm gonna present to you, I gave it first in the workshop that I did in Brazil in July. And it was a workshop called Imagining Interstellar Ices Across Art and Science. So it was a mixture of people that works for arts and people that were doing science. And because I am like an amateur photographer, I did a bit of both. So in the first part, so if after my talk, if you want to check the project, I did like doing my experiments in the lab. For 1 week, I took pictures for like in different steps of my day, and the idea was that I was going to track the systematic process of my experiments. So in each column that you see here is a different day of experiments, and you see that it's a bit messy, but yeah. So in the first row, for example, you see that they are very similar. And you can see the difference actually if you come closer later, that it only changes like my clothes are different from each picture. So actually for every row that you see here, they are very systematic, and the only thing that you can see as a difference between the pictures is my clothes. And can you play the video? Astrophysics in Leiden, which is a place that is known for studying interstellar ices. So during the night, during my talk, I will direct us, like conduct us of how I imagine the interstellar ices that we see in space. So with a laboratory perspective across art and science. And I usually like to start my presentations with a big question of why we do the things that we do, like in science in general. And for tonight's question, I have how do we imagine something we cannot see, we cannot touch, and that it exists in a place we will never go. And I know that Mathilde already introduced what is astrochemistry, and she did a really good job. But I did this meme and I really like it, so I want to bring it back. And so, yeah, what is astrochemistry and how is it different from astrophysics and astrobiology? And when we talk about astrobiology, it's actually, so basically it's the study of the conditions and the evidence for life beyond Earth. And when we talk about astrophysics, we are studying the physical process of stars and galaxies in the universe. And astrochemistry is actually a bit similar, and actually these fields, they of course they have overlaps and intersections, but astrochemistry specifically uses molecules as a tool to understand stars, planets, and galaxies. And these molecules are interesting for us. They are good tools because first, they are good tracers of the physical conditions of the environments where we detect them. We saw a few examples in the talk before. So they can give us like information about the temperature where they are, the density and the radiation field of stars nearby. They also are tools to uncover how stars and planets form, which for me is like the most beautiful part of this, because we can understand, for example, how our solar system was formed in the past. And they are also good samples of chemistry working at the edge, because they are in environments with a super high temperature or extremely low temperatures. So it's like how this chemistry works under extremely exotic conditions. And so in order for us to advance our knowledge in these topics, we actually have like 3 subfields inside astrochemistry, which is people working with observations, experiments, and doing chemical modelings. And it's a cycle that feeds itself. For example, we can have the detection of a molecule in space, and then we want to understand how this molecule is formed. Then we go to the lab, and I do laboratory experiments to understand how this molecule is formed. And then from the data that I get in the lab, we can put it in models, and then these models replicate the abundances of these molecules from observations. So it's really like a cycle that feeds itself. And what I'm interested in the talk, like what is my project at the moment, is so I contribute to the experiment pillar of this cycle, and I try to understand how complex organic molecules are formed in interstellar ice, and what do they tell us about star and planet forming regions. And so we can have like molecular detection in the gas phase. So in interstellar medium, so the medium between stars, most of the material that is there is in the gas phase. So 99% of the interstellar medium in mass. And more than 330 molecules have been detected there. And mostly of these detections is done by radio astronomy. But also, like the part that I'm interested is in the dust phase, so the solid part. So the solid part is composed by silicates, so like a mineral, so it's more like a mineral part, which is similar to, let's say, sand on Earth. And then this material, this dust, is also covered in the ices, which is the part that I'm most interested in. And this dust and the ice mantle is detected by infrared astronomy, but it's much more harder to detect these molecules in the solid state than in the gas phase. So just to have a comparison, about 300 molecules have been detected in the gas phase, and less than 20 in the solid state. So this brings me to, I'm gonna go back to this question like at least more 2 times in this talk. And but this comes to the first challenge that I have in the lab, which is we can detect the molecules in the gas phase, but observing them in the solid state is way harder. So I simulate possible formation routes in the ice, even for molecules that we are not yet sure that they are there. So how do I do this? And so Matilda already told you that we have like different physical conditions in interstellar space. And so, for example, in this picture, which is a really nice picture that we took like about 2 years ago with JWST, so the James Webb Telescope, we see that there are different regions of this molecular cloud. So for example, here we see like this blue black ground, and here we see a lot of material. We see like these darkest regions, and we can also like spot some stars that are behind this cloud. So the densest part of the interstellar medium, which is also the coldest, is these dark spots. So it's so dense and cold that light cannot pass through these regions. So in these regions we are full of interstellar ices. But for example, in some regions that are not so dense, we can see like some background stars behind. So here I don't expect to see much of interstellar ices. And so how do I imagine these interstellar ices and how do I replicate them in the lab? So I'm going to show you the view that I have in my field about how these interstellar ices are formed. And so in the diffuse interstellar medium, these places where we don't have a lot of density, so we have the bare dust grain, so without this ice mantle, and most of the molecules are in an atomic, like most of the species are actually atomic. Like we have hydrogen atoms, oxygen, carbon. And then when we start to increase the density of these clouds, the temperature starts to decrease because the radiation cannot penetrate in these clouds, so it's not possible to break the molecules. So the temperature decreases, the density is higher, and then we are able to form some molecules that are stable to stay in the ice. So they are freezing in this dust grain. So in this stage, for example, we have water being formed, we have ammonia, NH3, and CH4. And so this 70% of the water that we have in our body, or the water that we're drinking your beers right now, were formed in this stage. And the last stage that I want to talk about is, so after this layer of ice, if the temperature drops even more, like below 20 Kelvin, even the most volatile species starts to condense, so to freeze out on top of this ice. So CO, for example, is a very light molecule, and then it's going to condense, and then can be hydrogenated up to the formation of methanol. So it's a molecule that Mathilde told us earlier. So here we can have the formation of complex organic molecules in the ice. And a part of the formation of the molecules, we have a lot of process that can take place with these ices. So we can have like a thermal processing, so these molecules then can go to the gas phase and go back to the ice. We can have morphological changes, so the ice can be more disordered, but then they can crystallize over time. And can also have like an energetic process, so interaction with ultraviolet or X-ray photons. So how do I simulate all this process in the lab? So we are gonna go to the things I do in the lab, and I also come back to the second challenge that I have, which is I cannot simulate the perfect interstellar ice because interstellar ices are messy. They have like different layers. They can have mixed phases and processes happening with them. So I choose one target, one molecule, and I investigate how this molecule might form using simplified ices, so one variable at a time. And so these are the parameters that I'm usually interested to replicate in the laboratory. The first one is the vacuum, which per se is like a very philosophical question, but yeah. And so the vacuum that we have in the lab is about 10 to minus 9 millibar, which is an ultra high vacuum. And this is about 10 million times lower than the air pressure around us. But actually the interstellar medium vacuum where we are interested, like in these environments, it's about 1 billion times lower than the atmosphere on Earth. So we cannot, like it's 10 to the minus 15 and 10 to the minus 9. So you can question yourself now, like, Franciele, but this is a problem for you in the lab? And actually, it's not. So what I'm interested to replicate in the lab and what I cannot have in my ultra high vacuum chamber It's like a lot of contaminants being deposited on top of my ice. So if I have a lower vacuum, let's say 10 to the minus 7, I have one layer of water being deposited on my ice every 10 seconds. But if I have like a much better vacuum, so an ultra high vacuum, I have 4 layers being deposited every hour, and this is much better. And the parameter that this is important for me to replicate, which is similar to interstellar medium, is the temperature. So, for example, most of my experiments are depositing interstellar ice analogs at 10 Kelvin. But I can also replicate like some interstellar ices that are close to a star. Then I can reach temperatures about 100 Kelvin. And in the lab, to replicate these temperatures, I have this device that is called cryostat. So it works in a similar way of our air conditioning that we have in our houses. But the difference is that instead of having the normal gas of an air conditioning, I use a helium. So the helium can go to a much lower temperature, and I can reach the temperature in this surface when I deposit an ice in about 2 hours. So it's 10 Kelvin. And I'm always amazed that I can reach like 10 Kelvin in the lab. It's really cool, literally. And so the ice material that I have to deposit is a mix of gases. So you can have like molecular hydrogen, carbon monoxide, carbon dioxide. I can also deposit like liquids like water, or even like evaporate solids like to study the amino acids. And then I have injection lines where these gases are going to be introduced. And then I have like this mix of gases that are gonna reach the surface, which is very cold, like at 10 Kelvin. And then I form my ice on the surface of this device that is in the middle of an ultra high vacuum chamber. And then we have our ice. And then we can process this ice with different techniques. So I can increase the temperature over time. I can do some energetic processing with bombarding this surface with hydrogen, for example, or with photons. And I also have some techniques to probe the ice, so to study what's happening, like the reactions that are taking place on the surface. So we usually work with infrared spectroscopy, and we can also compare the laboratory spectra that we have in the lab with the spectra from JWST, for example. But since Matilda already introduced it, like spectra and observations, I actually just want to mention that the spectra that we have in the lab is we can turn it like it's wavelengths, so it's a wave. And we can turn it, this spectra actually also to a sound that we can hear. And so my two friends that are somewhere over there in the background, you're famous now, Marta and Łukasz. Marta is studying photography, and last year she asked me to participate on one of her projects, and she was picturing like the astronomy side of me. So you see me and a lamp in the background that looks like a star. And then Łukasz, which is observational astrochemistry in the Leiden Observatory, he took one of the spectra that I have in the lab and he turned it into a sound, like a music. And this sound is not going to work right now, but it's working. So it's very cute. We can turn the spectrum that we have in the lab to a sound that. So every peak that you see here becomes a musical note. So I talk about like these different parts of my instrument in the lab. And this is how all of the parts look when they are assembled. So this instrument is called Surface Reaction Simulation Device. So the acronym is SURFASITE. But actually for me, when this setup is working, I like to call it my baby. And when it's not working, I call it my little monster. So as I mentioned before, like we can have like the hydrogenation, so CO interacted with hydrogen and forming like new species like methanol, and this takes place like in the surface of dust grains. But I'm interested in understanding like different routes to form these molecules. And here I brought the periodic table of astronomers, which is, I am a chemist actually, and this looks boring, but actually gives a lot of information about the species that we have in space and their abundance. So the size of the atoms that you see here, it corresponds to their abundance in space. So the most abundant species is atomic hydrogen. Then we have helium and a minor abundance of other species. But for example, for molecules that are interesting for life, they just use it like most of them use hydrogen, carbon, nitrogen, and oxygen. So we can already replicate a lot of the complexity just with these atoms. But actually, what I'm interested in my fellowship in this project is to understand the reactivity of molecules of the species with molecular hydrogen, because yeah, hydrogen is the species most abundant, but only 25% is in the form of atomic hydrogen, and 75% is in the form of molecular hydrogen. So at the moment in the lab, I'm trying to understand reactions involving molecular hydrogen to form complex organic molecules. So for example, in the lab, I do a mixture of water, atomic carbon, and molecular hydrogen, and I can see the formation of methanol, which is the simplest organic molecule. But I brought this as an example, but the project that I am studying at the moment, and is also the experiments that I showed here, involves a sulfur-bearing complex organic molecule, which is called methylmercaptan. So it's an analog of methanol, but instead of oxygen, I have sulfur. And yeah, so I also brought this interesting fact that happens sometimes when we are working in the lab, which is I have this colleague, Katie, which was doing another experience involving sulfur. And it's a pretty cool experiment and study that you can check in her paper from last year. And she was studying like the formation of ammonium salts, NH4SH. And NH4SH was detected in a molecular cloud and also in comets. And she was doing NH4SH in the lab. And after she finished her experiments, she saw that one of her vacuum pumps was not working as it should be. And when she opened the filter that is connected to this vacuum pump, she saw a lot of sulfur crystals being formed there. And last year I was also in a conference in Japan, and we hiked a mountain that is called Sulfur Mountain. And there I found a piece of sulfur, which I also have with me tonight. So it's the sulfur rock is over here, and you can see that, yeah, it's the same rock. It's sulfur here and sulfur here. So this brings me again to this question of how we imagine interstellar ices. And I just want to make the connection that the same chemistry we test in the lab is also the chemistry that we found in a sulfur mountain or in interstellar space. So the same laws of physics and chemistry run the universe. And I know probably many of you are familiar with this phrase of Carl Sagan, that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apophytes, all these atoms are made of in the interiors of collapsing stars, so we are all made of the same stuff. But actually, I wanted to rephrase this and bring that we are made of interstellar chemistry, because the water that makes up to 70% of our bodies was formed in the early stages of star formation, and frozen onto ice dust grains in cold molecular clouds. And the amino acids that build our muscles and memories may have arrived on Earth aboard meteorites and delivered from space and already assembled. So we are not just made of star stuff, we are also made of interstellar chemistry. So the first people that I want to thank in this presentation is the people from the workshop where I first showed this, this talk. And I had a lot of fun. I'm actually from Brazil, and I was back to my former institute there. And I also want to thank my colleagues from the lab. And if you want to check in the QR code, there's a video of me reassembling this instrument that I have in the lab. So thank you very much.
We'll have some questions, I hope. Do we have some questions for Franciele?
Yeah, I have a question.
Yep.
So, towards the end, of course, you mentioned that the chemistry that you see, let's say here on Earth, you also see in the universe. But I'm curious to know, is there any part of chemistry that you expect to break down in the universe? Like, are you expecting any deviation in these extreme environments that you cannot find here? Is there any kind of unanswered question that you expect to find in these environments?
Yeah, so I think over my talk I bring the attention to some of the challenges that I have. And in the lab, for example, I don't know exactly what is the structure of the ice. So over the time we bring we collect some pieces of the puzzle of how interstellar ices are in space, and then I try to replicate these conditions in the lab. So, I try to replicate the conditions of, in the lab, of what we have in space, but these are definitely different of the chemistry that we have usually in the days, on Earth. So that's the difference. So, in the lab, I can replicate some of the processes that are happening in the space, and the processes that are happening in space are different from the ones that we have on Earth.
You mentioned there are 330 molecules that have been seen, and some of them have been amino acids already, or what is the most complex molecule that you know?
Amino acids, they haven't been detected, but not like in these interstellar clouds. They have been detected on comets and in meteorites. So comets, for example, they are in the solar system, and they are also samples of the material that was forming the solar system. So if you detect the molecule in a comet, we usually expect that we are going to detect at some point in the interstellar medium. But at this point, at this stage, amino acid is too complex to detect in the gas phase of interstellar medium.
How do you decide which molecules would you want to study in the lab?
Good question. So it depends on what's happening in the field at the moment. So for example, sulfur molecules, we did a lot of experiments with oxygen in the past, and now we are moving towards other molecules or other species that have not been explored. So sulfur-bearing species are one of them, like phosphorus-bearing molecules are also another. And people studied a lot of hydrogenation in the past, but now my interest is in molecular hydrogen. That is way more abundant than atomic hydrogen. So it depends on what's happening in the field that I can pick what's interesting for me.
I have another question. In the beginning you mentioned different methods, and I saw quantum chemistry calculation and models. What's the difference between those two?
Like the quantum chemistry calculations, they help me to understand if a certain route that I'm exploring to form a molecule in the lab is also viable, more in terms of the in terms of the calculation. So And then the abundance, the models, I use this data that I have in the lab to understand some abundance from the observations. So the quantum chemistry is for more reactivity, and the models is connected more to observations.
What sort of rates of reaction do you get in the process? Because you're bringing gases in and they'll react. Can you actually gate them quickly? Can you see the time, detailed resolution, how long the reaction takes?
Yeah, sure. Like, for example, this paper that I showed earlier from a colleague, there was a study in the formation of ammonium salts in the interstellar ices. She was depositing NH3 and H2S at 10 Kelvin, and then she was increasing the temperature of the substrate up to, let's say, 80 Kelvin. And just the fact of increasing the temperature, we increase the reaction rate. So we are favoring the formation of the molecules by the temperature. And then we also use like some techniques that help us to see this evolving.
I am very confused with so much chemistry around it. Why are they called organic? And why are like 330 molecules have been detected? But what is the Earth made of? Like the planet Earth made of molecules, no? And we have other planets somewhere. Aren't those molecules counting those 330 or?
They are already counting on this 330. So actually, so in the spectra that we have from exoplanets, for example, at the moment we can just like see more simple molecules that they have been already detected in other parts of the space. And by complex and organic molecule, we are talking about molecules that have at least one carbon and more than 6 atoms. So CH3OH is a complex organic molecule, but if I have like an H2CO, it's not considered as a complex because it has less than 6 atoms. So it's just like a matter of definition that we use in the field, because if you have a complex organic molecule, it's also like fainter and more difficult to detect.
And the carbon is the one that gives the name organic?
Yeah, the carbon. The presence of carbon and 6 atoms.
Time for one more quick question.
Yeah, you mentioned that at different temperatures you get different molecules crystallizing into ices, or crystallizing might be the wrong word, but so do they mix, or do they form layers, or grain structures, or how does that work?
Yeah, so that's a really nice question, because it also, like these different layers of interstellar ices in space also help us to understand what is happening in the interstellar medium and in the lab. So depending on the temperature of the molecule that is formed, we form different layers in the ice. So the first layer we expect that is full of water and ammonia, and then later we have CO that is more lighter, forming in the top. So so we have like different layers of the ice depending on the temperature.
Okay. Thank you very much again for a wonderful talk.